Hi everyone, thanks for coming. So as you can see, we're only deploying when the sun don't shine. If you're wondering why that is, it's because we don't really need to worry about deploying when the sun shines. We all live and work in the UK, so that's quite obvious. So yeah, who are we? I'm Simona. I'm a DevOps engineer here at Accurx. One of the most notorious skills that I have is being a pain about documentation. Less popular but still relevant, I am also the advocate of standardized monitoring and stress-free support shifts.
Hi, I'm Mitch. Is this much louder? Sorry. I am also a DevOps engineer here at Accurx. I was working in distributed systems programming for about 4 years. And at the tail end of that, I got into a lot of automation and cloud infrastructure. And so for the last 2 years, I've been quite interested in following that into DevOps. My goal is really to help develop a really good developer platform. And hopefully we can kind of cover some of that today.
What does Accurx do? Lawrence already covered the presentation, but just to recap, Accurx partners with the NHS to facilitate communication in between patients and their healthcare providers. As a company, we regularly do GP practice visits because as lovely as our office is, we're not going to learn much about our users if we're just sitting at our desks. And one of the key reasons why doctors hate their computers is that most software in healthcare is built by people who don't really know what happens in a practice on a day-to-day basis, and we can't fall into that trap. So, as DevOps engineers, our users are the product engineers. So, why should we go to practice visits? Well, our dear colleague Johnny mentioned that while on a practice visit, he discovered that when it's rainy outside, practices are way more crowded. And our amazing data scientist Patrick helped us to confirm Johnny's theory. And as you can see in the graph, the number of requests that we're getting for our patient triage product are roughly 12% higher when it's cloudy or partly cloudy, and 17% higher when it's actually raining outside. Okay, but what can I take away from this conversation as a DevOps engineer who works for the healthcare industry? People seem to forget that they are ill when it's sunny outside, and availability is crucial, especially during peak times. Now, keep that story in mind because we'll be coming back to it at the end of the presentation, but for now we'll walk you through the availability issues that we're facing and how we're mitigating them. So, how can we maintain availability? What actually feeds into that? A few aspects that we identified are monitoring, then is the way we do our deployments, and then how we recover our systems after a calamity. Let's start with monitoring. To give you an overview of our environment, we're using Azure for our infrastructure monitoring, we're using Sentry for our application monitoring, and Uptime for our service monitoring. On top of that, we have Slack, which captures all the alerts and the notifications. This has served us well for some time. Engineers have the freedom to join and monitor any channel related to their component. We had all eyes on our monitoring channels for a while, and we're also fans of Slack, as you can react to alerts with reassuring emojis. But catch-all Slack channels make ownership and action unclear for engineers. Then Sentry and Slack do not give us an easy way to provide standardized documentation. And defining priorities and escalation paths is difficult. And if we need to move to one out-of-hours support schedule at some point, being notified about everything is not ideal. So, what are the first steps that we took to mitigate these issues? Okay, so we've created a component map. As you can see here, we have mapped several Slack channels to the platform team. So every alert that will be coming in DevOps monitoring or Dev Kubernetes logs will be under the platform ownership. Next, we added common troubleshooting guides in the alert description to help with the first steps in a critical situation. And with dedicated classes and teams to Slack channel maps, we were able to move to self-serve monitoring, and now product engineers can configure the alert routes themselves for new services. So what have we learned from this? Defining monitoring ownership early is really important. That will ensure that alerts are actionable, and it will make it easier when it comes to defining the escalation path. You might want to set the troubleshooting process direction by creating documentation, because we all know how pressuring it is to work when alerts are flooding the channel. A few simple steps might drive the team into the right direction, and that can reduce the downtime. Last but not least, self-documenting code. That will make it really easy for teams to categorize their monitoring, and it will ensure that the alert ends up in the inbox of the team which has the most context to action it. I'm gonna pass the presentation to Mitch.
That click on? Mm-hmm. Okay. So once we've been alerted and we've noticed an issue, the most common workflow will generally require either rolling back a problematic change or deploying a new fix for the bug that we've encountered. The main components of our stack for this process are Git for our version control and Azure DevOps for our pipelines and our deployments. We found Azure DevOps to be pretty good because it provides a lot of features for customization, like templates to avoid the duplication between all of our services and our deployment pipelines. And it provides a good library of tasks for us to do the common things we need to get something deployed. And it integrates well with our permissions and our cloud infrastructure, which are also in Azure. So we've had consistent interest from our developer community about easily testing changes end to end. And we allow this in our dev environment with flags for some isolated testing. Here is an example of how a user can deploy a branch for testing with our Azure DevOps integration. So on the top left is the Azure DevOps UI. The user would pass in their GitHub branch, click down, give a fancy test feature name, and then that would be deployed onto our Kubernetes cluster as a separate isolated version running on its own pod with the domain name that they passed in as a variable. This functionality is provided, allows our devs to test features early, preventing some bugs from reaching end users and enabling parallel work streams on one feature or on one component that they're working on. But even with an isolated testing process, it's not foolproof, and we might need to roll back our changes. We found that the release discoverability is quite a bottleneck for our rollbacks because correlating a change with the growing number of tools that we use can be a bit difficult. As an example, to find the current release on our system, a user generally will either need access to logs or knowledge of the appropriate monitoring channel that error or log has come up in, access to a Bastion VM within our internal network on the cloud, access to the Kubernetes cluster that version of the software is running in, and potentially the ability to run kubectl commands to discover the currently running version of the source code on the pods. So we also have pipelines for each of these service components, which could consist of server apps, client apps, function apps, infrastructure stacks, automation pipelines and scripts. And that has resulted in pipelines on pipelines on pipelines as we've scaled as a company and consistently added new services. So it's kind of like trying to find a needle in a haystack when a problem occurs. If you've been around Accurx for a while, the process of deploying multiple services and their interdependencies can be a bit manageable if you have knowledge. But for someone that's new and not familiar with our tooling, it can be quite challenging. So recently, we've added commit IDs and origin branch names to our Sentry alerts. So the first point of call when an alert comes in, someone can click, see which commit it came from, and then follow that down to the Kubernetes pod, where we've also provided that commit in the metadata. And this enables users to follow a change from the Sentry alert all the way down to the underlying Kubernetes pod. But this is a temporary solution, as we realize that managing our deployments and rollbacks for components isn't really the easiest in our current system. without some prior experience of all the tools. And we're planning to streamline this process with a centralized deployment tool, which we currently have dubbed our Lord of the Pipelines. And hopefully it will be one pipeline to rule them all. With this mono-pipeline project, we'll also rework the branch deployments that I mentioned earlier. To give a little bit of background on how we currently do it, we use Nginx ingress rules and Helm to achieve what we were showing earlier. The solution has worked, but wasn't really scalable as we've added new services and extended our APIs. On the left here, this is what a developer would look at in the config file. It defines a bunch of paths that are exposed by each service, and it essentially says, for when I'm deploying this branch for this service, this is the other service I want to communicate with. And it means that the interdependencies have to be defined for each app that we want to test in isolation. So you can imagine about 10, 15, 20 of these in each of the config files. So it doesn't really, lend itself to ease of use. And Helm has allowed us to get away with this currently by abstracting some of the complexity away, because otherwise you would have to define CRDs for the Helm ingress rules. But Helm isn't the easiest thing to deal with when you're testing these changes, and the more we've added to it, the more complex the conditions have gotten for each individual app. So to avoid the hurdles and provide more power to our devs, we plan on leveraging a service mesh. Main features we're looking at are header-based routing, so we can kind of do away with all the Helm and ingress rules and just further the end-to-end testing capabilities by allowing devs to provide that when they're sending the requests. So overall, the lessons we learned is if there's a buggy release that ends up being deployed into production, making sure that the problematic commit can be discovered and rolled back easy is important. And by allowing our devs to deploy changes to an isolated environment is pretty essential to preventing bugs and the subsequent downtime that occurs. But what happens when you can't roll back a change? What do we do when the cluster has gone boom boom? And there isn't something, it's not something we plan on, but we need to be prepared for it. And that takes us to the disaster recovery. An example situation that we've encountered was we were testing Istio, a service mesh, and we decided to perform a routine upgrade of both of our orchestrator version and the control plane version of our Kubernetes cluster. We did that across all the clusters in dev, but what we didn't know was that Istio wasn't compatible with that version, and it completely broke the config of the cluster. And reverting to a previous version of the cluster wasn't really an option available to us through Azure's APIs. So what did we do? We just recreated the whole environment on the cluster from scratch. Some of that was pretty straightforward, updating our DNS and load balancers to turn off traffic and creating a new cluster via our infrastructure as code. We did this with C# and Pulumi, which is what we use in our stack, and have been able to abstract some of the components in the YAML config and allow us to make a one-line change to remove or add infrastructure components. So here's kind of a condensed version of what our YAML config looks like for our DNS, and we have a list of active IPs. By removing that line, checking it into source control and having someone review it, it'll remove the A record from our DNS, and that means that none of the traffic goes to the A cluster. We've tried to take a similar approach for the cluster's config itself by allowing and exposing some commonly changed variables, so the orchestrator version of the cluster, the size of the VMs, and then also we've gone down to the level of just listing a bunch of clusters and the name that we provide them, so we could add C, D, E to create 3 new clusters and run it through Pulumi, or we could just remove A if we know it's a problem and we've already removed the routing and just want to get rid of it. This has alleviated the likelihood of making mistakes and sped up the cluster recovery process. So configuring our Azure cluster seems kind of manageable, right? However, all of our cluster add-ons are a bit of a different story. We've grown to use an array of different extensions like Ingress Nginx, Istio, Queued, FluentBit, we have some cron jobs that are configured on our clusters. And so we're looking to improve the config's simplicity by regularly reinstalling all those extensions and trying to track the dependencies between each of them. Yeah, that's kind of what it feels like. And these cluster add-ons are really the only piece of our infrastructure in that part of the stack that we're not tracking in code. So, the cluster, the DNS, and everything else is in code, but not these. Not in the same way anyway. And you can see it here as an example. We have like one pipeline that uses Pulumi, deploys our Kubernetes cluster, but then we also have a pipeline for each extension, which uses Helm. And so in a disaster scenario, we have to run each of these in a particular order in order to get the cluster in a usable state. And so what we're going to do going forward is track them all in Pulumi. And thankfully, Pulumi integrates with Helm. So we end up just having a usable cluster after one pipeline run. And in our code, we can define all the dependencies between the tools, just like you would in any other kind of coding language. So this will speed up our deployment process considerably, as all the add-ons will be deployed with the cluster in one big chunk, and hopefully resulting in less human error during a disaster. Another takeaway from our Kubernetes mishap was to recreate our clusters on a regular basis. So for things like version upgrades, config changes, or anything that has like potential high impact to the cluster's config. And this has helped us ensure that we have more frequent deployments of the code that is actually tracking the infrastructure, and the configuration stays up to date. So to recap, the lessons we've learned are that deploying your infrastructure continuously will ensure that you're covered in a disaster scenario and confident to make a larger change. Sorry. And tracking as much as possible in code will mean that the more is tracked, the safer a change will feel when they're needed the most. And by exposing the commonly changed config, you'll avoid the complexity when making those changes. And I'll pass back to Simona.
Thanks. So getting back to the question at the start of this presentation, why do we, as DevOps engineers, need to visit the GP practices? Well, our goal as a platform team is to be aware of issues and have solutions to mitigate them before our end users are even aware of those issues. However, in some circumstances, there are no metrics and graphs that cover what our end users are really experiencing. And this is why, outside of our technical responsibilities, we commit to both GP practice visits to observe our end users and assist the support team with regular shifts. These experiences can provide a wider perspective and a more detailed view of the impact our changes can have. And at the end of the day, all of the aspects that we covered in the presentation influence the availability of our service. And all the operations that we discussed about do take a lot of time. As we're all aware, that can be translated into downtime in critical situations, and sometimes we just cannot escape it. What we can do for sure is to reduce that to the minimum, and we hope that our learnings will help you do the same.